All right, here's solutions problem 42 off the subject GRE math practice test. So in this problem, we have a set z plus here, so the set of all positive integers, and we define a metric. So you can think about this as like an idea of distance on this set. And the way we define distance, you think normally the set of integers and distance, like if I give you two integers, 3 and 7, you might say those are a distance of 4 apart. But that's not how we're defining distance. We're not using our normal distance metric. We're instead saying 3 and 7 are 1 apart, because the distance between any two elements in my set is always equal to 1 unless those two elements happen to be the same number. So sure, the distance from 3 to 3 is 0 as you'd expect, but the distance from 3 to 5, that's 1, not 2. That's my distance metric, which I'll be using in this problem. And so what I'm asked is, which of the following statements are true? If I take an element in this set, then the set containing only that element, or the subset, is an open subset of this set. Well, what you need to know for that is what the hell an open subset is. And you might have an idea when you think about an open subset. Maybe you're thinking something like this, which is true according to our normal metric. That's what you think of when you think about an open subset. All the numbers from 0 to 1, not including 0 and not including 1. The reason this works is by using this definition. A subset is open if for any element in the subset, so pick any number you want here. I don't care what you pick. You pick 0.9821. That's the one you picked. But you can pick anything you want. It's totally arbitrary. For any element in the subset, there exists a neighborhood about that element. So you give me this element, I give you a neighborhood about that element. So maybe my neighborhood is all the numbers from 0.9820 all the way from 0.9822. So you gave me an element in this subset. I give you a neighborhood about that element. Note that this neighborhood is contained completely inside this set. I could do that for any element of this set. Therefore, this set is an open set, or subset, I guess. So yeah, that works as long as we're talking about our normal distance metric. That same definition will work for openness. A subset's open if for any element in the subset there exists a neighborhood about that element contained completely in the subset. It'll just be a little bit tricky because we have a weird notion of distance. But let's think about what's going on here. I'm picking a single element out of this set. So this is all the positive integers. You pick one of them, 7, for example. And what this is saying is the subset containing only the number 7 is an open subset of this set. Well, is that true? Let's see. Let's go to our definition. A subset, so this one, for example, is open if for any element in the subset. Well, this subset only has one element, the number 7, or whatever the hell you chose n to be. So that's the only element that you can choose. That's the only element you can choose up here. You give me 7. Now what I want to do is I want to build a neighborhood about that element that will be contained completely in the subset. And you're like, how's that possible? If the subset only contains 7, if I make it any bigger, it'll spill out of that subset. Well, actually it won't. Because if I take, let's make my neighborhood is all elements within, I don't know, 0.5 of n. Right? That's a neighborhood. It's all the elements within a given distance of n, and that neighborhood will only contain the element n, or the element 7. So, in kind of a weird way, creating neighborhoods this way on this weird metric will tell me that this is an open subset, that this is a true statement right here. Every subset of this is closed. That'll end up also being true. What you need to know about that is a subset is closed if its complement is open. Okay, so I have a definition for open, and I have a way to figure out if a subset is closed. I think about its complement. Every subset of this is closed. Well, that's true if the complement of every subset is open. But the complement of any if I allow every subset, the complement of all those subsets is just all of the possible subsets. So this statement is true if and only if every subset is open, because any subset has a complement that is also a subset. So is every subset open? Sure, by the same argument that I did in 1. You give me a subset. Fine. My subset contains, I just got integers here, 1, 3, 5, 7, and 9. That's a subset. It's a great subset you chose there. Okay, now you choose any element in that subset. That's this right here. Maybe you choose the element 1. Fine. I'll create you a neighborhood around 1 that will be contained inside that subset, 1, 3, 5, 7. And I'll do it the same way I did it here. I'll say include all of the elements within 0.5 of 1. That'll include exactly 1, which will be contained within 1, 3, 5, 7. Therefore, it will be open. And therefore, the complement of that, which is a subset, will be closed. That makes this a true statement here. Finally, the last one. Every real valued function defined on this is continuous. Turns out that's true as well. It's kind of an interesting one. I don't know the best way to solve this. What naturally came to mind for me was epsilon delta. So if you've seen that argument, that'll work. If not, you could probably do it by drawing pictures and thinking about what it means to be continuous. You'll need some sort of definition of continuity. The epsilon delta definition says that if you are given an epsilon greater than 0, then there exists a delta, there's a weird looking delta, greater than 0, such that if the distance, so okay, this is really continuity at a point P. A function is continuous at a point P if, given an epsilon greater than 0, there exists a delta greater than 0, such that anytime the x-coordinate is close to P, how close to P should it be? Well, less than delta. That would imply that the corresponding y-coordinates, the f of x values, so f of P minus f of x, is less than epsilon. So the way you can think about this is you and me are playing a game. You choose epsilon to be this really, really, really small number. And then what I get to do is choose delta, some other number. And what has to happen is that anytime the x-coordinate is within delta of P, then the y-coordinates have to be within epsilon of each other. Yeah, that sounds right. So does that make sense? Well, let's see what's going on here. Every real valued function defined on z plus is continuous. This game really easily. You choose your epsilon that's really, really small. I don't care what the hell you choose. 0.0001, 0.1, 0.1000 zeros, then a 1, whatever. You choose some epsilon that's greater than 0 that's really, really small. I'll tell you what my delta is going to be. Without even caring about what your epsilon is, I can tell you what my delta will be. I'm just going to let delta equal 0.5. Because if delta equals 0.5, think about what that implies. If two numbers in my set, are within 0.5 of each other, that means the distance between them is less than 1. If the distance between them is less than 1, the distance between them has to be 0. If the distance between them is 0, those two values are the exact same value. So by forcing these two elements to be within 0.5 of each other, really I'm kind of cheating. I'm forcing these to be the exact same number. If these are the exact same number, then the difference in their corresponding y-coordinates is the exact same number. This distance is 0. Right? The difference between these two numbers will be exactly 0. And 0 will be less than whatever the hell you chose for epsilon, no matter how small you chose your epsilon, because your epsilon had to be greater than 0. So this is a true statement as well. The answer here would be E, because 1, 2, and 3 are all true statements.